The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. So today we're going to go on to section 11.4. I didn't get any emails with questions from section 11.3. So we'll just continue on. And let's see here. Let's say we had the following situation. 2 cubed is 8. And 2 to the 4th power is 16. What if we said 2 to the x power equals 12? What do we know about x? Well, x would have to be larger than 3 and smaller than 4. And we could sit there with our calculator and go through and guess and trial and error and eventually get an answer, 3 point something, whatever. But there's another way to go about it. And the situation here is we've got this exponential equation, but we need to solve it for the variable, which is the exponent. Okay. So what we can do, we can take this equation, 2 to the x equals 12, and use something called logarithms. We can rewrite this equation as log base 2 of 12 equals x. Now, unless you've dealt with logarithms before, this doesn't really mean anything to you yet. But what I do want to point out is that we've now isolated x. So if we could figure out what log base 2 of 12 is, which eventually we will be able to, we could then solve for x. And we'll come back to this situation. But the thing I want to look at here is how to take an exponential equation and rewrite it as a logarithmic equation. Okay, so 2 to the x power equals 12 is the same thing as log base 2 of 12 equals x. I want to talk briefly about an inning of baseball. In an inning of baseball, there are two teams. There's the team that's up to bat, and there's the team that's out in the field. After the team up to the bat gets 3 outs, the players on the teams change places. The players up to bat go out in the field, the players out in the field go up to bat. When they do this, do they pick up the bases that are in the infield and carry them into the dugout? I mean, we talk about stealing a base. No, not at all. The bases stay the same, but the players change places. What does that have to do with this situation we're looking at mathematically? Well, the way we say this is 2 to the x equals 12. 2 is the base, x is the exponent, but the point is 2 is the base. The way we say this expression is, for this equation, log base 2 of 12 is x. So in this case, 2 is also the base. But notice that the 12 and the x change places. So what we get here is the base is the same, but the players change places. Now, I want to point out something else, though. This is 2 raised to the x power. This is not 2 raised to the 12th power. So the relationships here are not the same as they are there, okay? But they're still together. Okay, now, a general statement that your textbook has, it says y equals log base b of x is equivalent to x equals b to the y power. Notice the base is the same in both cases, but the x and the y change their locations. All right, what I want to do now is take us through some problems where we're going to practice changing from logarithmic form to exponential form of an equation and from exponential form to logarithmic form. Okay, all right, so here comes the first problem. It says log base 3 of 81 equals 4. It says write each wrong. Logarithmic equation as an exponential equation. So this would be 3 to the 4th power equals 81. The base is 3 in both cases. The 81 and the 4 switch locations. Any questions on this particular problem?
No.
All right, let's take a look at another example. Log base 6 of 1 over 36 equals -2. So this becomes 6 to the -2 power equals 1 over 36. The base is 6 in both cases. The other two numbers change their locations. All right, let's take a look at another example. Log base 8 of the cube root of 8 equals 1/3. Changing this logarithmic equation to an exponential equation, we get 8 to the 1/3 power. Let's try that again. 8 to the 1/3 power equals the cube root of 8. Recall from chapter 9, the cube root of 8 is the same thing as 8 to the 1/3 power, isn't it? The index becomes the denominator of the exponent. All right. How about this one? Log of 0.01 equals -2. Well, there's something missing here. They haven't told us what the base is. And here's the deal, okay? Log base 10 is commonly used in mathematics. So commonly used that this is referred to as common log. And mathematicians decided that they would be efficient. And if it's log base 10, we're just going to write LOG. So if there's no base written down here, we assume it's base 10. In fact, on your scientific calculator, there is a button, or should be, that says LOG, log. And if you look at it, the second function is 10 to the x, which would remind you that log is equal to log base 10. So what does all that have to do for this problem? Well, there's an assumed 10 there. So now this would be 10 to the -2 power equals 0.01. You still might question, well, is that true? Well, isn't 10 to the -2 power the same thing as 1 over 10 squared, which is 1 over 100? And 0.01 is 1/100th. So it works. All right, let's take a look at some other equations. X equals log base 9 of 81. So this would be 9 to the x power equals 81. The base stays the same. The players change places. How about this one? N equals log base b of r sub 1. B to the n power equals r sub 1. All righty. Any questions there?
No.
Now we're going to go the other direction. We're going to take some exponential equations and write them in logarithmic form. For instance, 8 squared equals 64. So log base 8 of 64 equals 2. 10 cubed equals 1,000. Log base 10 of 1,000 equals 3. I want to point out this could also be written just like this, because with no base written, a 10 would be implied. Okay, and let's see, how about this one? 1/3 to the -3 power equals 27. So log base 1/3 of 27 equals -3. And finally, how about this one? 12 to the -2.6 power equals n plus 1. So the base is 12. The other two quantities are -2.6 and the quantity n plus 1. Now, this would be log base 12 of n plus 1 equals -2.6. But there's something I've forgotten here, okay? All of this needs to be grouped because the way I had it before the parentheses, the log base 12 of n plus 1, the 1 wouldn't be attached with that log function. So we need parentheses around the n plus 1 in that context. Okay. Now it says solve for x. If we have log base x of 9 equals 2, that would mean that x squared equals 9, right? Well, if x squared equals 9, we could take the square root of both sides and we get x is plus or minus 3. So x equals -3, x equals 3. There's a problem, however. And let's go back to, let's see, is it the day before? Yeah, when we talked about exponential functions, exponential equations, let's say of the form y equals b to the x, we said that the base had to be greater than 0 and it couldn't equal 1. Okay? The domain would be all real numbers from -infinity to +infinity, but the range was greater than 0. Take, for instance, a basic graph like this. Okay, so the domain, all real numbers, the range greater than or equal to 0. Okay, so again, the base has to be positive but not equal to 1. X, the exponent on the base could be any real number, but the final answer has to be greater than 0. Okay, so what does that mean for the problem that we did here? The base has to be greater than 0 and not equal to 1. So the base can't be -3. So even though solving this equation, we came up with a -3, it doesn't fit the original scenario. So be careful of that situation. Okay, now, let's see here. Log base 7 of x equals 0. Solve this equation. Well, if we, let me say this. If we have a logarithmic equation and we're trying to solve it, most of the time, not all the time, but most of the time, you end up changing it to an exponential equation in order to solve it. And if you have an exponential equation where you're trying to solve for the exponent, most of the time you end up changing it to a logarithmic equation in order to solve it. So let's change this logarithmic equation into an exponential equation. It would be 7 to the 0 power equals x. Well, what is 7 to the 0 power? It's 1. So x equals 1. So log base 7 of 1 equals 0 because 7 to the 0 power equals 1. Okay, let's see here. Log base 4 of 16 equals x. Changing this into an exponential equation, we get 4 to the x equals 16. Now, something we did, I think, let's see here. Is that earlier on? Maybe not. Okay. Let's do this. I guess we didn't cover this in a previous section. I was thinking we did, but if we have an equation like this and we can write it so that both sides of the equation are the same base raised to a power, for instance, 16 could be written as x to the, 4 to the second power. We can then go the next step and then say, since the bases are equal, the exponents are equal, therefore x equals 2. You okay with that?
Yes.
All right. How about this one? Log base 3 of x equals -4. So here we get 3 to the -4 power equals x. Well, 3 to the -4 power is 1 over 3 to the 4th power, which is 1 over 81. So x equals 1 divided by 81. Okay. And let's see, this one's a bit tricky. How about log base x of 1,000th equals -3/2? So we've got x to the -3/2 power equals 1/1,000. Okay, now recall that when you have a power raised to a power, you multiply the exponents. I want this equation to be x equals something. So if I take both sides of the equation and raise it to the -2/3 power, what is -3/2 times -2/3? It's +1. So x to the -3/2 power raised to the -2/3 power becomes x to the 1 power, or just x. But now on the right-hand side, let's see, 1/1,000 to the -2/3 power would be 1,000/1 to the +2/3 power, which is just 1,000 to the +2/3 power, which is 1,000 to the 1/3 power squared. What's the cube root of 1,000? It's 10. What's 10 squared? It's 100. So x equals 100. A lot of review there. A lot of review. Okay. Let's see here. How about this one? It says log of x, excuse me, log base x of 9/4 equals 2. So we get x squared equals 9/4. If we take the square root of both sides, we get x equals ±3/2. But again, the base can't be negative, so it's just going to be x is 3/2. Okay. Questions? We doing okay? All right. This says evaluate each logarithmic expression. Log base 3 of 9. Now, I don't know what that's equal to, so I'm going to call it some unknown box. Okay, log base 3 of 9 is whatever would go in the box. But now I have a logarithmic equation. And if I rewrite it as an exponential equation, I have 3 to the box power equals 9. I could write 9 as 3 squared, therefore the box is 2. So log base 3 of 9 equals 2 because 3 squared is 9. Okay, there. Let's see here. Log base 1/3 of 1/81. Well, we'll say that equals box. So 1/3 to the box power equals 1/81. Oops. That looks like a 7. Let's try that again. But 1/81 is like 1/3 to the 4th, right? But isn't 1 equal to 1 to the 4th power? Because 1 to the 4th power, 1 times 1 times 1 times 1. So this would be equal to 1 to the 4th over 3 to the 4th, which would be equal to 1/3 to the 4th power. So now 1/3 to the box power equals 1/3 to the 4th power. So the box is 4. So if I can manipulate to where I get the same base on both sides, then the exponents are equal as well. That has to do with the fact that they are one-to-one functions, which we talked about earlier in this chapter. Okay, let's do some calculator calculations. Let's find the log of 0.57 using the calculator. Remember a few minutes ago, I said there was a button that said LOG. When I push that button, I get that. So then I'm going to put in 0.57, close it up, and it equals -0.24412514443. And we were asked to write it to 4 decimal places, which would be there. The 2 would round down. So I get negative 0.2441. Any question about that?
No.
All right, let's do another one. Let's find the log of 375.876. So again, log button, I get that. I'm going to put in 375.876 and close it up. And I get 2.57504, etc. But 4 places, the 4 would round down in the 5th place. So 2.5750. All righty. Here is an application problem. Okay. It says stocking lakes, as in putting fish in lakes. A farmer stocked a lake on her property with 75 sunfish. She was told that with the proper oversight, the sunfish population could be approximated by the logarithmic function f of t equals 75 plus 45 log of t plus 1. Now notice there's no base written on the log, so we're talking log base 10. Okay. This function where t is the number of years since the lake was stocked. Find the number of sunfish she can expect in a lake in 2.5 years. So t is 2.5 years, or how about 2.5 years? So f of 2.5 equals 75 plus 45 log base 10 of 2.5 plus 1, which is 75 plus 45 times the log base 10 of 3.5. So going to the calculator, 75 plus 45 times log base 10 of 3.5, and I come up with 99.48. So we're going to say about 99 sunfish, because 0.48 of a fish is not going to live very long. Okay. Any questions there?
No.
Look at another example. It says children's height. The logarithmic function h of a equals 29 plus 48.8 log of a plus 1 gives the percent of the adult height of a male child. A years old, of a male child, a years old has attained. In other words, so if we put in the child's age, the boy's age for A, we get what percent of their adult height they've obtained. Okay, or attained, it says. If a boy is 9 years old, what percent of his adult height will he have reached? So h of 9 is 29 plus 48.8 log of 9 plus 1, which is 29 plus 48.8 log of 10. Okay, so 29 plus 48.8 log of 10, and I'm getting 77.8. So that would be 77.8%. So they're saying that on average, a 9-year-old boy has already reached 77.8% of his adult height. This doesn't mean this is true in every case, but you know, they did this with a whole bunch of people, I suppose, and determined that on average that was what was true. Okay, let's do one more here. Let's see here. Investing. It says if P dollars is invested at the end of each year in an annuity, earning annual interest at rate R, the amount in the account will be A dollars after N years. Don't worry, I'm going to read all this again, where N equals the log of A times R over P plus 1 divided by the log of 1 plus R. Okay. N is the number of years. A is the amount that will be at the end of the account, at the end of time. R is the annual interest rate. And I think I already said P is the principal. Okay, it says if $1,000 is invested each year, okay, so $1,000 would go down there for P, earning 12% annual interest. So that means that, let's see, P is 1,000. Let's do this. R is 12%, which is 0.12. So that means we're going to have, oh, and then it says, and the account is worth $20,000 at the end. I should have just written all this down to start with. So up here, A is going to be 20,000. R is going to be, so that's going to be times 0.12, and then plus 1 all the way over there. And then on the bottom, we're going to have 1 plus 0.12. Okay, so A is 20,000, R is 0.12, P is 1,000. Down in the bottom, R is 0.12. Okay, so let's clean this whole mess up. On top, if I take 20,000 times 0.12 divided by 1,000, I get 2.4. And then that's plus 1. So that's going to be the log of 3.4. And on the bottom, I get the log of what, 1.12. So basically, I've got the log of 3.4, close it up, divided by the log of 1.12. And I get 10.79846138, but it says round to the nearest tenth of a year. So the 9 would round up. So it'd be 10.8 years. Any questions on that?
No.
Okay. Well, that's all I have for you today. So tonight, your homework 11.4. Tomorrow, we'll look at section 11.5. Wednesday, we'll do 6 and 7 in the review. Thursday, we'll review. Friday will be the chapter 11 test. And then next week on Monday during class, we'll review, and then your final exam is on Tuesday. So the end is near.
Oh no. Mr. Mayo, I have a question.
Yes.